Presentation we'll have Stefan Arsenault, and this presentation is entitled CFD Simulations with VULCAN-CFD. Stefan is a rising junior at Robinson Secondary School in Fairfax County, Virginia. He's been working on computational fluid dynamics software under Dr. Richard Ball.
Thank you. All right, good morning everybody. My presentation, as Brittany said, is entitled CFD Simulation with VULCAN-CFD. First, I want to go over what is CFD. According to Wikipedia, CFD, computational fluid dynamics, is it's a branch of fluid dynamics that uses numerical analysis to solve and analyze problems involving fluid flows. Basically, this means that people doing CFD are going to use mathematics to predict the way fluids like air or water move throughout a system, right? So that sounds fairly simple, right? It's not. In practice, CFD is a lot more complicated than that. At the core of CFD are a series of three equations, differential equations, known as the Navier-Stokes equations. These are the Navier-Stokes equations. It's a little bit intimidating. As you can see, there are actually three of them. One of them simulates movement across the x-axis, one of them simulates movement across the y-axis, and one across the z-axis. And these equations, they take into account a large number of factors, and solving them by hand with any degree of accuracy would be nearly impossible, right? So how then do we solve them? We use models. So most flows of engineering interest are going to be what's called turbulent flows. And these have a wide range of length and time scales that must be resolved. So we can't do that necessarily for every single time scale. So we have to use a series of models basically to make assumptions and simplify down the problem for us. So here's an example of one of the models that we use. This is called the Spallert-Almas model. It's still, fairly intimidating. It's a differential equation, but it's a lot simpler, you can see, than the Navier-Stokes equation. So there are different levels of model complexity that can be used. This is what's called the one equation model, excuse me. As you can see, there's only one equation. Whereas something like this model is called Mentor SST. It's more intimidating than Spallert, but it can still be solved by a computer fairly easily. This is a two equation model. You can see it has two equations. And basically it relies on the additional equation to make its predictions. So where does VULCAN come in? VULCAN is a software package designed to model the movement of fluids by solving the Navier-Stokes equations with these models. Basically, VULCAN is a very, very complex calculator that can be used to solve these equations to predict how the fluids are going to move throughout a given grid. So here's an example of a VULCAN case. You can see air is coming in through the wider area, and it's being compressed by the nozzle, which accelerates it, and it's being shot out at the end. It's being shot out toward the end there at roughly Mach 2 or so, and it's coming in much slower than that. And then here's one that I actually ran called the transonic bump. And you can see we have air coming in on this boundary, flowing through here and hitting this bump down here. You can see there's a shock wave that occurs when the air hits the bump. You can see it goes supersonic, it goes supersonic for a moment there. Yeah. So this is a pretty neat one that I also ran. It's a simulation of airflow through a nozzle. You can see again, air is flowing in through here. It's compressed by the nozzle. It accelerates outward and goes almost supersonic, or almost sonic, I should say. Interestingly, these nozzles, things like this, you can see the acceleration is how they get wind tunnels moving as fast as they do. They have the air flows in through a nozzle, which compresses and accelerates the air, and then it flows back out into the wind tunnel, and the fast-moving air you can use to test against your test item. So how does it all work? Vulcan has an input file that it's a long input file that contains all the assumptions that we want Vulcan to make regarding the simulation. So these include things like Mach number, what Mach number we want our air to flow in at, the heat of inflowing fluids, pressure, viscosity, and so on and so forth. It also includes what model we want to use. Here is an example of a section of an input file. This isn't the whole input file, but you can see we have variables we want to output here: density, velocity, Mach number, pressure, temperature, so on and so forth. And then down here we have assumptions we wanted to make. So for example, we wanted to say that the inflowing air was traveling at Mach 0.875, that our temperature was 300 degrees Kelvin, things like that. That's under the reference conditions. Also, interestingly, is here you can see we specified what model we want to use here. In this case, we're using Mentor SST, which is that one, the two-model equation. So that's the one that Vulcan will use to solve flows. So in addition to the input file, Vulcan requires what's called a grid file. Basically what this does is it takes a CAD file, a computer-aided assisted drawing, and it turns it into a series of cells, which are similar to like an Excel spreadsheet, just a lot more complicated, where, and basically these cells you can, excuse me, the software calculates the models. It runs the models inside each cell. So the more cells you have, the more accurate an output you're going to get. So for example, smaller grid cells are desired in regions where flow properties are expected to vary drastically. So if I have basically at the area of interest, I'm going to have very small grids, and outside of that I might have larger ones. Here's an example of a grid file. You can see this is for a similar problem to the nearsonic jet that I showed earlier, this one. And you can see here, these boxes are cells, and you can see that as you get closer to the green section of the grid, the cells get much smaller and smaller. And interestingly, as you can see on this, our grid is split into 3 separate sections. This is because if we have it split into 3 sections, we can actually utilize 3 processors in order to calculate the grid, in order to run Vulcan faster and run the models. So the simulation process, this is the process basically of designing an engine and running it through simulation. Step 1 is an engineer designs a 3D CAD model of the geometry. Basically that means he's going to create a 3D model of his engine or his airfoil or whatever it is he's designing that he wants to use a simulation software on. Then the engineer is going to take this CAD model and he's going to run it through a software that will create a grid, just like this one, for his CAD. Then he will create a input file for the CFD simulation that's basically going to say, this is what I want, this is how I want to run my simulation, these are the assumptions I want to make. This could be, if he's running something at high altitude, it could be colder air. If he's running something, it could be lower pressure, things like that. Depends on how he wants to simulate it. Then he's going to execute the CFD software, which is Vulcan in this case, on a large-scale parallel computer systems, which basically means a powerful computer that will then get the performance metrics, which will tell him He can plot it against a grid and create a image like that and get all sorts of graphs related to performance of the engine. And then if the results aren't acceptable, you can use the simulation to change his geometry of the engine, change how it's going to work, or the airfoil, until he gets it to a point where it's good enough for him. So what was I working on? We've covered a lot of VULCAN-CFD and how this all works, but what was I actually doing? So for the past 4 weeks, I've been working on a process called validation. Basically what this is we take the results of CFD software and compare it to theory or experimental measurements, basically other sources, if you will, things that have actually been run through the wind tunnel, and we have data that we're 100% sure of. And we compare our results against that to ensure that the models are accurately reproducing our flow, basically to make sure that the models are working for our given situation. So over the past 4 weeks with validation, I've been working on automating the validation process. So I've been writing a script that makes it much more efficient with the end goal of basically completely validating the process, or excuse me, completely automating the process. Our script was designed to do 2 things. One, it was designed to streamline the process of running the validation simulations, make it easier to load in the input file, set it up, and actually run it. And 2, to automatically extract the necessary data and compare it against experimental data. So once you've actually run the simulation, our script was designed to extract the data that we wanted to compare against what we already knew to be fact to ensure that it was working. In order to streamline the process, we designed a script so that it was intelligent enough to automatically adjust the input deck. So imagine we were trying to run, say, a case called the turbulent plate case, and we were trying to validate the Spallert-Almas model, right? So we run our case, all good. Then we decide that we want to run the same case using a different model. Maybe we use Mentor SST. Using the script we could write, rather than actually going into the input file that I showed you guys in the previous slide and typing Mentor SST instead of Spallert-Almas and changing it manually, taking time. The case tells the program, okay, the user has inputted that he wants to solve the case using a different model, so automatically go in and adjust the input deck accordingly. Right. So this is a screenshot. It might be a little bit hard to see, but this is a screenshot of our program running. You can see I say validate VULCAN for this case number 5, and then it provides me with a list of transport of models that I can use in order to solve for this equation. I chose model number 1, which is the power law. It then runs that case for model number 1 and outputs the data. And you can see it successfully runs. It says VULCAN validation for velocious plate.dat succeeded. Velocious plate is the case that we're running. So now that it's successfully run, we're ready to compare results, right? We have our data, it's been run through the model, and we just need to make sure that it's accurate according to our experimental data. So, the next part of our software is designed to extract the data we need. So it takes the plot files that are outputted by VULCAN, and it runs it through our plotting software, and extracts the necessary data in order to get a grid like this. So, the program in this case outputted 2 graphs. This is the first one. It's comparing velocity along as a function of distance, and you can see the dotted lines here are experimental data, so that's what we know to be true. And the red line there is what we got running VULCAN according to the power law model. So you can see that it's a very accurate representation of what we know to be true. So this is the next one. We're plotting here friction coefficient along a specific x value of our graph. You can see again the theory, or the experimental data is in dots, and the theory that we're running through Vulcan is in red. You can see again, very accurate. It's adhering to it quite a bit. So where do we go from here? In that example, it was only one case. The great thing about our script that we wrote is that if you want to add a case, you can add a case. It's as simple as adding an if statement. And everything is completely set up so you can just automatically run as many cases as the user wants to load into the program. So here you can see this is just the sort of manual page, if you will, for our script. You can see down here that we have seven cases loaded into Vulkan by default. Those are the shock oblique, expansion fan, shock tube, Vorteisen, Blasius plate, another similar Blasius plate case with slightly different in the turbulent plate case. And so all the user has to do is go in and just edit the script a little bit to add another case. All right. So I just wanted to finish up by saying a few words about Governor School. What I've learned here has been awesome. It's been great. Having the opportunity to work in Dr. Barrow's lab, learning about CFD and engineering, I feel like I've gained a lot of skills that will help me throughout my life. Also, I've learned a great deal about CFD. I came in knowing nothing about CFD, and I left knowing, I feel like, at least a lot more than I did going in, which is good. In addition, for Governor School outside of work, I've learned about some opportunities that I'm hoping to pursue this year. I have some things like science fairs, things like that, I had never really thought of, and talking with the people here has given me interest in doing these sorts of things. It's also opened me up to the world of internships. I didn't know anything about this before, but yeah, so hopefully next year will be an even better experience. So, thank you. Do we have any questions? No questions? Yes.
I have a question.
Oh, sorry.
Go ahead.
Were the models that you were running, were they for 2D flow or 3D?
So the way Vulkan works is that I believe, if I'm not mistaken, it takes a 3D equation and it simplifies it to, or a 3D grid, and it simplifies it to a 2D grid.
Well, all the cases you did were that way, just so they would run quicker.
Yeah.
But it can't be run in 3D.
Yeah.
In real world, it's typically 3D, but for this process to get solutions quicker so we can actually make progress.
Yeah. So, yes, those cases were all 2D, but like he said, Vulkan does have the capability to run 3D. Yes.
So what was the hardest learning curve, since you said you didn't have any experience with this before?
Well, I've done programming in the past, so that wasn't too hard. I'd say the hardest things I had to do were learning to set up the input deck, because I didn't know any of the terminology, all that stuff. It took me a while to figure that out. And then also, this is something I still haven't quite figured out, setting up the macros for our plotting software. I'd never worked in anything like that before, so yeah, those were the two hardest things, I would say. Yeah.
So VULCAN-CFD, is that open source?
It is not open source, unfortunately. I think if you go to the website, it's vulcancfd.larp.com, I believe, or .gov. You can look up VULCAN-CFD and the website will come up. I think you can file a software request, but I'm not sure that students are able to get it that often, just because of reproducing the code and giving it to people and stuff like that. But I guess you could try.
It used to be what's called ITAR, only available to U.S. citizens, and recently got downgraded, but NASA is choosing to still protect the codes as if they were ITAR, just to be on the safe side. So bottom line is, it would be students can get it definitely if they're working on a project or having a grant with NASA or some other government agency. But if a student just wants to code and play with it for they will probably decline.
But there are open source versions that they can get some practice on.
Yes, there are other open source CFD software codes available.
I guess Autodesk, CFD, stuff like that. All right, do we have any other questions? Yes.
So how do you see CFD fitting into any engineer's life? You said that you had this experience with it. Is it something that anybody who wants to go into engineering should be familiar with?
I think
and where
at
do you
least-
see it heading in the future?
I think at least aerospace engineering, definitely. So, for example, the application, I was working in the hypersonic air breathing propulsion facility. So that's ramjets, scramjets, things like that, which are engines that basically, if you didn't have CFD, you wouldn't be able to make a scramjet engine, because the way they work is the air comes in, it's compressed, and it's pushed out. So there's no actual moving parts in a ramjet, it's all movement of fluid flows. So I think CFD is a very important piece of that equation, if you will, that whole project. Yeah, does that answer your question? Okay. Any other questions? No? All right, thank you very much.